Hello everyone, Mr. Waz here, and welcome to WasleyScience. This is part 2 of electricity, and in this lesson we are going to talk about series and parallel circuits, as well as magnetism and electric motors. So let's begin. So in every circuit there is a voltage source, a wire connector, and one or more devices that use the electrical energy. So the voltage source is usually like a battery of some sort, and that puts the volts in. The wire conductor provides the pathway for the electrons to travel, so there can be current. And then the one or more devices which use the electrical energy, those are the resistors. So those are the things that you count ohms for. So the first series we're going to talk about is a series circuit. And a series circuit is not very common in our world. The only time you see a series circuit is for Christmas lights, actually, because they're one of the few things that we see that provide a single pathway for the current to flow. So you've probably heard of the saying with Christmas lights, when one goes out, they all go out. And that's true, because if you snip the wire somewhere, all the lights will turn off, whereas most things around your house, if one thing burns out or one wire breaks, the rest of your house is still working. So let's take a look at this diagram down here. We're going to start talking about how to properly draw a circuit. So what we can see here is that a battery is drawn with two lines, essentially. One line is smaller than another line, and the smaller line is usually on top of the bigger line. So this is how electricians draw out a circuit. It's funny because I remember last year when we went over this and explaining it to students, and they thought that these 4 lines were one battery, but there's actually 2 batteries shown in this diagram. So this bigger line and smaller line is one battery, and then on top there's actually an additional battery in this diagram. So it's not really the best example for you to know, but you should really note that this of what I'm circling right now is one battery. So make sure that you do that when you make your own circuits. And then this boxy area here, that is just the wire. And I know it would seem kind of weird to see wire hooked up like so boxy like that, but electricians like to set it up that way, so it's very simple to add more and more upon it and see it in sort of a grid way. So the wires are, of course, not boxy like that. Like you can see in this picture here, the wires are not box shaped, but this is how we draw it, and that's really important. And then we have 2 light bulbs here, like as you see in the picture. The light bulbs are just circles with little swirlies in the middle of them, and they provide our resistance. So the light bulbs are what resist the current to flow through. The battery provides the voltage, and the electrons travel through the wires and provide the current. So let's take a look at this series example here. So one thing I didn't note before is that the smaller line on the battery symbol is actually the negative terminal. So this is where the flow of electricity is going this way. So it's going out through the negative terminal and then around and back to the positive terminal. And the positive side is the longer line. So in also this example, you can see that the resistors or the light bulbs or whatever kind of resistors they are not the circle with the zigzag or swirly through the middle. It's just these zigzags. So sometimes you will see the resistors drawn like that. Don't be discouraged. So anyway, in this you can see here that you can actually calculate the amount of current that's going through here. Let's say that the battery is creating about 9 volts, which is like a standard battery. And we got 2 resistors here. We have one with 80 ohms and one with 33 ohms. So if you do 80 plus 33.3, you will get 113.3 ohms. That's what you do when you in a series circuit, is you just add the resistors together to get the total resistors. And then it's 9 volts, so you just plug it in our little triangle here. You can use the same triangle method that we did with density. We have VIR, very important raccoons, volts, current, resistance. So anyway, if the volts is 9 volts, and the resistance is 113.3, you can just divide that and then get your current in amps. So you can go ahead and try that now and see what you get. Our other type of circuit is called a parallel circuit. And parallel circuits are what your house is all wired as, because it allows for multiple pathways for the current to flow. So if one of the pathways are broken, then the current can still flow through the rest of the pathways in your house. And it also allows you to individually select what lights or whatever plugs you want on and which ones you want off. So by allowing multiple pathways, you're allowing the current to have more options where to flow. So what makes this really interesting is if you have a series and a parallel circuit next to one another, like in this example here, you can see how the parallel circuit, within the parallel circuit, the lights are much brighter than they are with the series circuit. See how dim they are in this picture? So they both have 2 lights on them. They both have the same voltage of battery, but when you wire the circuits allowing multiple pathways, you can have more current, which would allow the bulbs to then be brighter. The bulbs are producing the same resistance. The only difference is how it was wired. Think of it this way. If you have a highway and you only have one lane on the highway, then all the cars have to go through the same lane. So that could slow down the flow of cars. But if you have a highway with multiple lanes, then you can allow more cars to flow. So the cars kind of represent the electrons in this example. So by allowing more cars to flow through, or electrons, you can allow more electricity, which could then let the light bulbs be brighter. So now that we've talked about parallel and series circuits, let's talk about open and closed circuits. Open and closed circuits is something that you could have with either a series or a parallel circuit. So a closed circuit is one in which the pathway of the electrical current is complete and unbroken. And what this means is when you have a closed circuit, you have set the switch so that you are connecting all the wires together, so your lights or anything that's hooked up to that switch can in fact turn on. And an open circuit is one in which the pathway of the electrical current is broken. And what I mean by broken doesn't mean that it's unfixable. It just means that your switch is off. And when your switch is off, your lights are off. So this is very confusing for a lot of people, because they think, oh, an open circuit, that means open for business. And when your business is open, of course, your lights are on. But it's not like that. It's backwards. When you have a closed circuit, that means your lights will turn on, and then you can, in fact, be open for business. So make sure you don't get caught in that sort of misconception. I'm sure you've had the situation in which you've had a thunderstorm and you needed to go downstairs into your basement or garage or some section of your house and play around with the circuit breaker. So what happens with this is when the path for electricity is unsafe, your circuit breaker will switch so that electricity can then not flow through while your home has an unsafe connection. And so, this may happen with a thunderstorm because there may be some lines that go down, but then the electricity will still be able to make it to your house, so you have to reset the circuit breaker to turn the lights on back in your house. If you have a really old house, you may have a fuse box. So maybe your grandparents or something have a fuse box. So the fuses can burn out, and then you have to replace the fuses, and it's kind of annoying. So that's why a circuit breaker is much more preferred. But with a fuse box, you may see that in cars. A lot of cars have fuses now, so you have to replace a little fuse if something in your car breaks. I've had to do that before. So let's move on to magnetism. Magnetism is a lot like static electricity when we were talking about static electricity in part 1. So magnets have a north and south pole. That's what the N and the S stand for. Magnets don't become charged like things that do when you add electrons to them, like when we rubbed the balloon in our hair and our head became positively charged and the balloon became negatively charged. Magnets don't really do that, but they are the same kind of force that static electricity is. So when you look at a magnet, no matter how many, you can cut up this magnet here or here or here into tons of little pieces, but no matter what, they will always have some sort of north and south pole. So just like static electricity, like with the protons and the electrons, the north and south pole are attracted to one another, and if you took another piece of magnet and tried to put the north pole to the north pole, they would repel each other. And same thing with the south pole to the south pole, they would repel each other. But put two magnets with the north and the south pole, opposites attract and the magnets would stick. While we're on the subject of magnets, and this is Earth Science class, I think it's pretty important to note that the Earth is actually a giant magnet. And this is really important. The iron nickel that we have in the core of our Earth gives the Earth itself this magnetic field around us. And it's really important for helping us navigate as well as protecting us from solar flares, which could burn us all. So yeah, magnetic field around Earth is kind of a big deal. I know I keep saying the word important, but without it, we would all be pretty much burned up. So one terminology to be familiar with when we talk about magnetism are magnetic domains. So when you have a substance like iron, cobalt, nickel, which are all metals, and I'll say now that not all metals are actually magnetic, but those three are. So when you have something like an iron nail, and you look at it, you really can't see it, but there's actually tons of little regions of north and south poles that are composed of billions of atoms. You can see that the norths and the south poles aren't really aligned with each other. It's quite random because there's no other magnet next to that iron nail. But if we took a magnet and we put it next to the iron nail, like you see in the right here, what will happen is all the norths and south poles of those domains or regions of billions of atoms will align themselves opposite to the magnet. So you can see here that all the green S's, which represent the south poles of the domains on the nail, are all on the top because the north pole of this magnet is on the top. And all the red ends, which stand for the north poles of the domains within the nail itself, are on the bottom because that's the south pole of the magnet. So it'll align itself opposite and all align themselves together. Alright guys, so now let's relate electricity with magnetism. How are they related? Well, when you have a wire like this gold wire that you see here, there are magnetic field lines around the wire. And the direction that the magnetic field lines are going depends on the direction that the electrons are flowing through the wire. And this is very important. This is why we have electricity. This relates to every single type of electricity that we have except solar power. Let's talk about an electromagnet now that we know that when you have electrical wires, you can create magnetic fields. So an electromagnet is when you take something that isn't naturally magnetic. Like magnetite is a mineral that is magnetic. It's a rock that's magnetic. Let's say we take a piece of iron and we take an electrical wire and we hook a battery up to it so there's electricity flowing through the wire, and we wrap it around the iron bar like as you see in this picture here. So as you wrap the iron core with wire, and let's just say there's a battery right here too, the closer you wrap those coils, all those magnetic fields that are around the wires are going to kind of combine and make a strong magnetic field to the point in which the bar now becomes a magnet. So to review magnetism, go ahead and click on the video here. It's the same guy that does Crash Course Chemistry. He also does a YouTube channel called SciShow. So he can help you review magnetism as well. And we're going to be talking about electromagnets more when we do the electromagnet lab in class. Alright, we're going to finish this lesson with talking about electric mortars. So with this diagram here, what we're trying to do is we're trying to use this battery which harnesses our electric energy, and we're trying to get this bar right here to spin. We want it to give us mechanical energy which would make it spin. So in this situation, we have the electricity passing through the negative terminal of the battery and coming up to what these two plates are called. They're called brushes. And so the electrons will approach the brush and then jump on this wire here and go around all these coils and eventually come to the end of the coil, then pass to the other brush and then back to the battery. Now a lot goes on during that time though. So this big blue curve here, that is called a permanent magnet. So the north pole of this magnet is always the north pole, and the south pole of this permanent magnet is always the south pole. But that's not the situation with the metal bar that we have in the middle. You're going to see these poles, the south pole and the north pole, which you can't see the north pole, but it's on the other side here. You're going to see those poles switch, so be ready for that. So we call this whole area here the electromagnet. So anyway, like we've said, the electrons are flowing through all these wires and they're producing a strong magnetic field which makes the electromagnet have magnetism. So this south pole here is going to want to approach the top of the permanent magnet because opposites attract. And then the north pole is going to want to move down. So just remember that as I go to the next diagram, that this whole electromagnet is going to be sort of spinning clockwise. So now you can see that the arrows here are kind of showing the animation of the magnet spinning. But what happens is when the north pole to the electromagnet aligns with the south pole of the permanent, and the south pole of the electromagnet align with the north pole of the permanent, the brushes spin as well, which causes the poles of the electromagnet to switch. And that's the big part there, is that the poles, the brushes, cause the magnetism of this electromagnet to switch. And when it switches, that means that now the north pole is aligned with the north pole. The south pole now becomes the north pole. So the north is with the north and the south is with the south. So what happens to a magnet when you have that situation? It repels. So it launches the magnet to continue to spin. And then when that happens, the brushes then turn again. And when the brushes turn again, it causes them to attract and then repel and then attract and then repel. And it repeats that sort of pattern. And that causes the electromagnet to spin continuously. And that's how an electric motor works when you have a sort of battery hooked up to it. Now, I know what you're thinking right now. You're probably thinking, when the heck would I take a battery and hook it up to some stupid bar and make it spin around a blue thing? Why is that useful to me? Well, I got news for you. Electromagnets are used on everything. Anything that you can imagine that involves some sort of spinning has an electromagnet inside of it. So instead of a battery, it's hooked up to the grid. It's hooked up to power lines and hooked up to your house. But on the other side of it is the spinning thing. So if you open up a fan, you'll find an electromagnet hooked up to the blades. If you open up an air conditioner, you'll find the same. If you open up a wash machine, you'll find the same. Go ahead and try to open up a car. You'll find electromagnets all over the car. There's tons of electromagnets on a car. What we're talking about here with this, blue thing and this electromagnet and spinning around, it seems like a small concept, but it really is a big deal. So we just talked about taking electrical energy and transferring it to mechanical energy so that you can have stuff around your house to spin. But can you take mechanical energy and convert it to electrical energy? And the answer to that is absolutely, because that's what's inside of all power plants. You have the steam turbine, which that is spinning because combustion of the coal, oil, natural gas causes the steam turbine to spin. So there you got your movement, and connected to the steam turbine. So I want you to imagine on the other side of this picture is the electromagnet. So the electromagnet, which is here, is on the other side of the steam turbine. It's connected, and the electromagnet is inside of a magnet. So while it spins, it causes electricity. So all you have to do after that is just hook up wires and power lines and such to the electric generator, and that is how electricity is made. So let's take a closer look at it. So in this example here, instead of a battery, you have a person rotating the electromagnet. And think of these two red spots here as the brushes in our last example. So from the electromagnet spinning, it causes the north and south pole to switch, which causes electricity to flow through the brushes, and then we have a wire that just completes the circuit. So we create a closed circuit, and by creating a closed circuit, the electrons can flow through and turn on the light. So that's really all what's going on here. The only thing that you may need to notice is that the electron flow switches back and forth as the north and the south pole of the electromagnet switch as it gets rotated, but the light will still stay on. Alright, one more thing I want to talk about before we end this. Direct current versus alternating current. AC versus DC. So what's the difference? Direct current is when electrical current is supplied by a battery, and that's the really important part. So if we ever use a battery, it's DC. So there's a constant flow of electricity, and it's only going in, here's the key, one direction. Alternating current is what all our power lines and electricity to our houses. So alternating current is electrical current which comes from a generator, and that generator is located in a power plant, and it involves what we were just talking about with the steam turbine spinning the electromagnet hooked up to the permanent magnet, and it causes the current to alternate back and forth. And so all our power lines, the electrons aren't actually traveling through the power lines. They're actually just moving a little bit left and right, left and right. That's what they do all day. But their movement is able to send electricity through our house, kind of like how a Newton's cradle works. Credits to some of the content on this presentation goes to Mark Richards. Alright guys, we did it. We got through electricity. So I know that was a pretty tough unit for you, so I got 4 videos here to help you review. If you click on the top left, you can learn about series and parallel circuits. He actually uses the same animation program that we'll be using in class. If you click on the top right, you can review on how electromagnets work. If you click on the bottom left, you can review on magnetism. And if you click on the bottom right, you can watch a video on Nikola Tesla, who we're going to watch a video in class, but this is an additional video which is also very interesting. Alright guys, thanks a lot and take care.